So unraveling magnetic fields in subsolar systems. Well, so our first contributor talk for the second half of the session is going to be by Enza, talking about the X-ray radio dichotomy of ultra-cool dwarfs.
Yeah, thank you so much. So hi, everybody. My name is Enza Magaudda, and I'm a postdoc at the University of Tübingen. And today I'm going to talk about this dichotomy in the X-ray radio data from the ultra-cool dwarf. So just a very brief information that we all know. The formation of the magnetic field from satellite to cool stars, it's what we are trying to understand in detail. So we have information about the solar-like stars, so FGK main sequence stars, where we know that the magnetic field is powered by the alpha omega dynamo model. We have no information whatsoever in detail about what happens when we go towards the cooler objects. So specifically for fully convective M dwarfs, so late spectral type later than M3.5, towards later on for ultra-cool dwarfs and brown dwarfs. So one thing to investigate that, observationally speaking, is to study the magnetic activity in the atmosphere by the flux variability at different wavelengths. And what we did in this project is to have the focus on the formation of the flares. So specifically, the flares are formed explained by the standard solar flare models. But without going into the details, we just say that this is a consequence of the magnetic reconnection phenomena. So basically, the convective buoyancy form the coronal omega loops, and then the rotation stretch and wrap the magnetic field lines, and they eventually break and reconnect, emitting energy in terms of the electrons that are accelerating along the magnetic field lines. And once they reach the foot points of the coronal loop, we had flares in the optical, in the ultraviolet, and in the X-rays. But at the same time, in ultra-cool dwarfs, so in very late and later spectral type, we also have evidence of coherent radio emission that are typical of the atmosphere of giant planets. So basically, we observe auroral emission where these radio bursts are caused by electron cyclotron Meissner instability. So in large scale magnetosphere, the electromagnetic radiation gets amplified by non-German electrons that are trapped in these magnetic fields. And we can see the X-ray flares, so magnetic reconnection phenomena, and radio bursts in the ultra-cool dwarf. Already in the past, by Stelzer in 2012, there has been a proposed scenario of a dependence with the rotation period, where basically ultra-cool dwarf that are slow rotating shows radio upper limits, but they appear to have a flaring activity in the X-rays, while for fast rotating ultra-cool dwarf, it was the opposite situation, suggesting a possible situation when we deal with strong field versus weak field. Later on, in Pinetas in 2012, there has been the study of the fraction of detectable radio emission as a function of the DSNI measurements, where indeed this scenario was much more visible for faster rotator. So for this project, we investigated what happened in the very short regime of rotation. So we selected a new ultra-cool dwarf sample, so new simultaneous X-ray and radio data with mostly photometric period within 1 day. And we also added 10 new ultra-cool dwarf from the literature with spectral type toward later up to L0, 5. So first thing, we implemented the activity rotation relation that you find here on the left. This is coming from my previous work, only for M-dwarf, so until M7, where you can see the two different regimes, the saturation, where the average X-ray luminosity is almost constant with the rotation period, and above 10 days, we are going the unsaturation when there is the correlation with the period. When we include the ultra-cool dwarf sample, this new one that I just mentioned, we can see that they are placed along the whole range of the activity rotation relation, suggesting that the activity is somehow disconnected by the rotation, probably because of the fact that we are dealing with cooler objects, that they have a neutral atmosphere, so the atmosphere is decoupling from the magnetic field. While investigating the X-ray luminosity versus the radio luminosity, we obviously use the Gödel-Lindens relation as comparison that I remind you is a study based on wider object, because we are talking about young and solar-like stars, algal type and Arscandan. And what you see here, there are a lot of symbols, but basically these are all the ultra-cool dwarf of the new sample studied with their quiescent emission, both in radio and X-ray. That could be also an upper limit. And the open square are the radio burst, and the upper star are the X-ray flares. So what we can see is that the ultra-cool dwarf are placed at radioluminous with respect to the GB relation, and that the X-ray activity is happening, on the other hand, closer to the relation. And we can also see this behavior in terms of the rotation period. So here is the GB relation, while we study the radio over X-ray luminosity ratio. And we can see that there is a separation around 0.2 days, that this is the translation of the Wiesenai threshold that was studied in Pineta 2017. And we have a distinction of a radio loud regime, where indeed we see the highest amount of radio bursts, and the radio quiet regime when we see mostly flares. There are still some objects that they present both X-ray and radio bursts, and also optical. There are the open square, and these are indeed these are indeed M7 stars. So it's like dealing with a transition in the magnetic behavior across the M spectral class. I also show you a peculiar case that we found in our project for the LP 42331 ultra-cool dwarf. In this object, we included the Rosita data, the satellite that has been launched in 2019 from the German-Russian consortium, where you can see that we detected variability along 2 years of observation. And at the same time, when we looked at the light curve in the radio band, we observed these two peaks here that are spaced by 2 hours, that this is way lower than the rotation period we have found, way shorter than the rotation period we had found from test light curve. So this suggested that there was something else rotating with a different velocity that, thanks to the inclination, we were able to detect. And we proposed that this could be indeed an auroral emission like for giant planet. And I'm actually very early because I'm already in highlights. Just to bring the highlights at home, as I said, with the study of the activity rotation relation, we can see that the X-ray emission of ultra-cool dwarf is not related to the relation, to the rotation, possibly because of their cooler atmosphere. And for what concerns the X-ray and radio variability, we observe X-ray activity closer to the GB relation, so closer to the behavior of the more solar-like type stars. And they are overluminous in radio, but we also observe this bimodal dynamo mechanism for ultra-cool dwarf for dichotomy, where indeed we can see that there is a magnetic reconnection with large-scale dipolar topologies. And with that, I thank you for the attention.
Welcome to Enza. So, one thing I remember from
Okay, so my question kind of clear about 2 hours, and is it possible to interpret this like fixation of gravitational axis or something like this? Because it is kind of like, looks like during this conference, most of the results interpreted like auroras, but maybe something else.
But I'm not that into the radio data. I'm not the person who actually analyzed those, but I don't think that the resolution of the instruments will give this information of the precession of the rotational axis.
The question just different interpretation, not just aurora.
From this light, I mean, this is not periodical, and also like this is just a variation of the light curve, and here in this circular polarized flux, and we see no variability. So I would expect that if something related to the rotation, you would have also observed it in emission, not just in the light curve here.
It's
transitional objects, what do you imagine the situation to be? So sometimes these ones look more cell-like properties, and sometimes they look more like round worlds. Is it a temporal thing? Like they sometimes behave like that, and they, for some reason, build up a corona temporarily, and the thing's right there. Or is it spatial, like, I don't know, at the poles, got a corona, and then the rest of it is sort of brown with clouds? How do you do it? What is it?
And this is the thing that we want to address actually, that like, because we are talking about a multipolar configuration, right? Multiple configuration of the magnetic field to a dipolar one, right? Like going from a magnetic reconnection scenario to a planet one. So it could be like here, considering the orientation of the system, it cannot be a reason of self-occultation or stuff like that, because we are able to see both simultaneously. So it has to do something with either the internal condition of the star, like this, the stellar characteristics, as I was saying, the temperature, the changes towards the spectral type and the couples, the magnetic fields, or it has to be with something related to the dynamo. And we go into a scenario that is not known yet, only through models and stuff.
Again.
Hi, Queen. This is Maria Rosa. Can you hear me? Hi, Queen. Can you hear me?
Yeah, Marie, we can hear you. Sorry, we can't hear you in the
Excellent.
room, but just give us 1 second.
Excellent. So, are you presenting
Sure.
the slides? I mean, are you moving the slides, or should I share my screen?